Good afternoon. The topic of my report is Dynamic Random Access Memory based on fiber optic lines for optical computers, computer modeling. I will begin with an introduction to our study. The appearance of optical fibers with low losses and a large product of length by bandwidth is opening up prospects in optical signal processing. It becomes possible to create fiber optic devices when performing operations such as convolution, calculation of correlation functions, matrix operations, filtering, pulse generation, code combinations, pulse compression, and matched filtering. However, the dynamic storage of light pulses for optical computers and optical information transmission systems is very relevant. Potentially, a light beam can have a spectral width comparable to its carrier frequency. A basic element of an optical dynamic operational storage device can store both analog and digital optical information. So, the basic element is a ring-type storage device on a fiber optic line, in which information circulates in the form of a burst of optical pulses along a closed fiber circuit. All the variants of optical dynamic random access memory proposed in well-known publications have a limited speed of about 10 gigabits per second. The aim of this investigation is a model study of the physical parameters and characteristics of a variant of implementing a dynamic optical random access memory device based on fiber optic lines for optical computers with a speed of more than 10 gigabits per second. This figure shows the block diagram of the basic element of the dynamic optical operational storage device on fiber optic lines. During the inquiry, we have obtained equations which specify the main parameters of the dynamic optical operational storage device. This slide presents limit operating parameters of the basic element of the dynamic optical operational storage device. Now, let us discuss results of the investigation. Computer modeling aims to confirm the possibility of implementing the software package Synopsys OptSim for optical communication, which is a program for modeling fiber optic systems, to perform the research. This slide shows a generator that forms a digital information sequence, a transmitter, an optical filter, an attenuator, a receiver, a tester, a spectrum analyzer, and an oscilloscope. This slide depicts the waveform and spectrum of the signal input to the fiber and the signal at the output of the optical signal receiver. Next slide illustrates the scheme for the study of losses. This slide shows the waveforms of the transmitter and receiver and the eye diagram. The effect of polarization mode dispersion is studied according to the scheme shown on this slide. These are the signal characteristics. Here you may see that non-zero dispersion shifted fiber with a negative chromatic dispersion compensates for the effect of polarization mode dispersion at a distance of 33-35 kilometers, which can be used to build a dynamic optical operational storage device on fiber optic lines. This schematic was used to study the power level to be input to the dynamic optical operational storage device. The initial parameters of the signal source are as follows. This slide presents the eye diagram at a signal source power of 10 milliwatts. Next slide shows the eye diagram at a signal source power of 50 milliwatts. Thus, at an input power of more than 10 milliwatts, a nonlinear mode of operation occurs in the fiber, which leads to distortion of the stored information. To conclude, I would like to say that the results of computer modeling confirmed the possibility of implementing the dynamic random access optical storage device based on fiber optic lines for optical computers. To reduce optical losses in a dynamic optical random access memory, it is advisable to use the operational range of 1515 nanometers. To compensate the polarization mode dispersion, non-zero dispersion shifted fiber of SMF-LS type should be used. A semiconductor optical amplifier can be used to restore the optical signal level. Optical signals are inputs and outputs through an electro-optical directional coupler. To work with optoelectronic memory on fiber optic lines, it is recommended to use a femtosecond fiber laser and the wave coding method. In further research, we will develop an experimental model of a dynamic optical random access storage device based on fiber optic lines for optical computers. Relevant experimental studies will be performed. We plan to compare the results of experimental studies with the results of computer modeling and draw conclusions about the prospects of the proposed dynamic optical random access storage device based on fiber optic lines for optical computers. Thank you for attention.